Jai Hind everyone. I am Shraddha Mishra, Assistant Professor, Garg Engineering College, Department of Information Technology. Today I am here to present my second lecture on discrete mathematics. Our topic for today is graph theory. So let's proceed. Graph theory and combinatorics. So graphs, these are the topics we'll be studying today, which is definition and terminology, representation of graphs, multigraphs, bipartite graphs, planar graph, isomorphism and homeomorphism of graphs, Euler and Hamiltonian parts, graph coloring. And in combinatorics, we're going to study introduction, counting techniques, pigeonhole principle. Let's proceed. So, what is a graph? A graph, if we talk about discrete mathematics, it means it's a collection of points called vertices and lines between those points. So as soon as we say graph, so the first thing which comes to our mind is it's a collection of points which is connected by edges. So that's a graph. So you can have a matrix and you can represent that matrix in form of graph, and different other representations can be done in the form of graphs, which we will treat further. Alright, so if you see here, it's a pair where you can see GVE, where VVG is a set of vertices, EEG is a set of edges. Example, VSU, VW, XYZ, and edges here are X and V. Now, parallel edges, two or more edges which join a pair of vertices and joined by two parallel edges are the parallel edges. For example, these two vertices are connected, here A and B, and C and D connects parallel to AB, so these are parallel edges as the name suggests. Loops, so loop is like a self loop here for the point D which starts and ends at the same point, that's a self loop. These are just the basics we are quickly brushing up, then we'll come to the main topics. Simple graph, a graph without loops or parallel edges is a simple graph. A weighted graph is if we put weights or we label the edges with a certain denomination, then you can say that it is a weighted graph. Next, a directed graph, if we put an arrow to the edges which we can read as from A, the edge is going towards F, that's a directed graph. Inward edges, so for point A, this A to F is an outward edge and this from D to A is an inward edge. Next, terminologies again for an undirected graph, we have the endpoints and we have the degree of vertex. So, degree of a vertex means if it is an undirected graph, so degree means the number of edges which are incident on that vertex, it's a directed graph. On the directed graph, that is the degree. Pendant vertex, degree of a vertex, if it is 1, it's a pendant vertex, as the name suggests, like a pendant we have. So you can see that for that vertex, the degree is 1, there's only one incident vertex to it. Isolated vertex, if there is degree 0, it's isolated, just a point in space. Representation examples, you can see here that degree of vertex, degree which has a if any vertex has a degree 1, this is how you represent it, degree V is equal to 1. Now, next is examples if you see. So, here is a representation. If it is an outward, it is denoted by plus. If it is an inward edge, it is denoted by minus. Next, here again have a self loop, multigraph. A graph which allows more than one edge to join a pair of vertices is called a multigraph. So, we can see here it's a multigraph. Since different edges, A is connected to D, A is also connected to C, is also connected to B, as we can see here. So, this is a multigraph right here. Next, we can see a simple graph, right, as we read there is no parallel edge or a self loop. Non-simple graph, if there is a graph like this, there's one vertex but there are no edges, so that's a trivial graph. Null graph, it's again a graph which has a point in space. Now, pseudograph, a graph having loops but no multiple edges is called a pseudograph. So, if you see this graph, it definitely has loops but it has no multiple edges. degree of a vertex, if we see this, we can see for this vertex, we have these 3 edges incident. So we can see for the V2, there is degree 3 because there are 3 edges which are incident on this particular vertex. So what is it? It has the degree for V2 is 3. Next, minimum degree and maximum degree. So minimum degree we find, and the maximum degree, so minimum degree is denoted by this del and maximum by this delta. Now we can see next is, you can see here in the example pendant vertex, right? So you can see V1 and V4, since these are the endpoints, so they are here the pendant vertex because there's only one vertex which is incident on it. Now we talk about the complete graphs. So a simple graph G in which every pair of distinct vertices are adjacent is a complete graph, and Kn has exactly n minus 1 by 2 edges. So in a complete graph, there's an edge between every pair of vertices. As the name suggests, it's a complete graph, means there's going to be edge between every pair of vertices right here. Order of a graph. So if the graph is a finite, the number of vertices denoted by V, and you put it under these edges. So that is what the cardinality of the vertex set V of G, the order of G. So the cardinality of the vertex set V of G is the order of G. Size of a graph, right? Like you can see here, there are vertices, these are edges. So if you talk about this GVE, okay, so you can see here you can represent the vertices and edges in this form. Okay, let's start with the first example. Draw a simple graph with 3 vertices. So graph means a collection of vertices and edges. So you can randomly draw a graph representing the problem 3 houses, 3 utilities, right? So you know, if there's a house and there is utilities, let's say water, gas, electricity, then all are interconnected definitely, right? So you can see here we have interconnected this. So we have these 3 houses, water, gas, electricity, and all these interdependencies within each other for the different houses. So this house 1 has water, it has gas, it has electricity. Similarly for house 2, it has water, it has gas, it has electricity, and same for this, right? So it finds our application in real life also. You can represent your utilities in form of graph. So if you see here an example of a simple graph, then you have a pseudo graph and we have a multi-graph here. Next, another example. So this is a formula which says that the sigma of degree vertices is 2 times the edges. So a non-directed graph G has 8 edges. Find the number of vertices if the degree of each vertex is 2. So if the number of edges is given to us and we have to find a number of vertices given the degree of one vertex. So this is the formula we use. Sigma degree Vi is equal to 2E. Now here if you see the sigma, so they're talking here. So edges is given as 8, which we have written here E as 8, right? Now, so degree of each vertex is 2. So here its degree of vertex, so we have used with the formula 2 we have done since the degree was 2 given, and hence we have a formula. So the number of vertices is 8. So if you have the count of number of edges and if you have the degree of a vertex, then you can most certainly find the number of vertices there. Now, adjacency matrix of a non-directed graph. Okay, so from the graph we can create a matrix, and from the matrix we can also create a graph. So let's just read about it. If you see here in this graph, if you see this adjacency matrix, you can see there is 1 and 0. Now 1 means there does exist a edge between the two vertex, and 0 means there's no edge between it. So this is an adjacency matrix and you need to create a graph for it, or from a graph create a vertex. So the number of vertices, you first list it in this matrix. After listing it, you can see for A and A there is no self loop, so we've written 0, right? For A and B, if you see here there is an edge, so we have written 1 for it. A and C, it is 0, right, because there's no edge, but for A and D there's 1. So similarly, we are going to fill this matrix. After filling this matrix, you can see that consider diagram shown here. The adjacency matrix is again given here, Okay, so similarly in this question, now here adjacency matrix is given and we have to create a. So if you notice here, in adjacency matrix, let G be the graph with n vertices and no parallel edges. The adjacency matrix is n into n symmetric binary matrix AG, Aij, n cross n. The adjacency matrix AG for graph G with n vertices is symmetric. The principal diagonal entries are all 0 if and only if G has no self loop. Ith row sum and ith column of AG is the degree of Vi. Now, if you see this matrix, so similarly, because this is a directed matrix 1. Now, if you see this matrix, you can see that the number is not just 0, 1, but 3 and 2 also, because it is an undirected graph. So, once you have an undirected graph, we just don't list 0 and 1, we list according to degrees. For example, if you see here for this point V1, there is a self loop 1, 2, 3, right? So, there are basically 3 edges for it. So, that's why for V1, we will list down 3. So, what is a multigraph? A graph which allows more than one edge to join a pair of vertices is called a multigraph, right? So, okay, now coming to the most important topic, which is bipartite graph. As the name says, bipartite, you can partition it, you can into two parts, which is bipartite. You can separate it into two parts, that's a bipartite. Now, there are a number of special classes of graph. One example is a bipartite graph. We now introduce few more graphs. So, a graph G is called a bipartite graph if its vertex set V can be partitioned into two disjoint subsets A and B such that every edge in G. So, if I partition it like this, you can see here, this is one part, this is one other part, right? So, you can partition it bipartite. You can partition it into two parts in such a way that the two subsets, which is A and B, in that every edge in G joins a vertex in A to a vertex in B. So, a bipartite graph can have no self loop. Okay, complete bipartite graph. A bipartite graph G in which every vertex of A is adjacent to every vertex in B is called a complete bipartite graph where A and B are partition subsets of the vertex V of G. So, you can see here, if I show you, this is a complete. Why? Because every vertex of A is adjacent to every vertex of B, right? It's all adjacent here and you can also partition it. Star graph, a complete bipartite graph K1n is called a star graph. A graph is said to be planar if it can be drawn in a plane so that no edge cross, it's a planar graph, right? You can also spread it into regions. Now, alright. So, next is about homomorphic graphs, right? Okay, so before that, let's come to isomorphic graphs. So, there are different types of graph: planar graph, isomorphic graph, homomorphic graphs. Now, when we come to the isomorphic graph, you can see in this graph, right, there's this GV and G star V star E star. They are said to be isomorphic if there exists one-to-one correspondence, that is, this vertex V maps to this and correspondingly such that UV is an edge of G if and only if F of U, comma, F of V is an edge of G star. So, number of vertices of graph A must be equal to graph B, that is one-to-one correspondence, same goes for edges. So, if the edges and vertex when we map, they are corresponding to each other, we say it's an isomorphic. What do you mean by homomorphic? Two graphs G and G star are said to be homomorphic if they can be obtained from the same graph or isomorphic graphs by this method. The graphs A and B are not isomorphic but they are homomorphic since they can be obtained from the graph C by adding appropriate vertices. So, homomorphic is you can create a certain graph from these two, right? So, if you can obtain the same graph or isomorphic graph by this method, okay? So, these are homomorphic. So, let's understand with the help of an example right here. So, you can see here for this phi of A, there is A1, phi of B, there is C1, right? For A, we have A1, for B, we have B1, for C, we have C1. So, correspondingly, we have the vertices. Clearly, the mapping is 1 to 1 and onto. This preserves the adjacency, and we can see here G star is an isomorphic. Note that both G and G star have 7 vertices and 14 edges each. Every vertex is of degree 4, so it's absolutely mapped. That's why we can say here that these are isomorphic. Similarly, here every vertex can be mapped accordingly. Now, Euler and Hamiltonian graph. A graph is traversable if you can draw a path between all the vertices without tracing the same path. Based on this path, there are some categories like Euler's path and Euler's circuit, which are described here. So, Euler's path. A Euler path contains each edge of G exactly once and each vertex of G at least once. A connected graph G is said to be traversable if it contains an Euler's path. So, if you see here what it means in simple words is a Euler path contains each edge of G exactly once and each vertex of G at least once. So, a Euler path means it was going to traverse every edge at least once, right? Exactly, so it's going to traverse each edge exactly once and each vertex at least one. That's a Euler graph. U is like 1, right? So, every edge it has to traverse only once, but vertex at least once it has to traverse, right? And a connected graph is said to be traversable if it contains a Euler path. So, if you see Euler path here, if we have to traverse this entire graph all at once without traversing any edge more than once, then how do we start? If you see here as they're written here, D, C, A, B, D, E. So, this way we are able to traverse this entire graph 1. So, Euler means 1. U is 1. So, you have to traverse all the edges only once, but vertices can be more than once. So, that is a Euler path for this. Now, Euler circuit, very obvious. So, any circuit which contains a Euler path is a Euler circuit. So, in a Euler path, if the starting vertex is same as its ending vertex, then it's called a Eulerian circuit. Circuit is always a closed one. So, it begins and it ends at the same point. It's a Euler circuit. For example, I started with this point and I'm able to traverse this entire graph all at once and have not even traversed any vertex more than one. So, that's Euler path. And if you see, we started with the same point, we ended the same point. Hence, it's a Euler circuit. Okay, Euler circuit theory. A connected graph G is traversable if and only if the number of vertices with odd degree in G is exactly 2 or 0. A connected graph G can contain an Euler's path but not an Euler circuit if it has exactly 2 vertices with an odd degree. So, here's a short trick. If you have an odd degree, it can never be a Euler circuit. Right? So, connected graph G can contain an Euler's path but not an Euler circuit if it has exactly 2 vertices with an odd degree. So, if there are 2 vertices which have odd degree, then it might not have Euler circuit here. You can see this Euler path begins with a vertex of odd degree and ends with the other vertex of odd degree. So, started here, but it had to end like somewhere else, right? So, it started with here, but it ended at this. So, it can't be a Euler circuit. Alright, so if you see that path, it's not an Euler circuit, but if it is an Euler path, clearly it has exactly 2 odd degree vertices. Now, we come to another most important topic, which is Hamiltonian graph. A connected graph is said to be a Hamiltonian if it contains each vertex of G exactly once. Such a path is called a Hamiltonian path. So, if you see here, the catch here is if it contains each vertex exactly once. So, in Euler, it was U means 1, means every edge at most once. So, it has to traverse every edge only once. In Hamiltonian, it has to traverse every vertex just once, right? And edge can be done number of times. So, if you see here, E, D, B, A and C, right? We are able to traverse this graph right here, which says E, D, B, A and C. Euler circuit contains each edge of the graph exactly once. In a Hamiltonian cycle, some edges of the graph can be skipped. Our goal here is Hamiltonian, Ham. It's like vertex. Okay. So, Hamiltonian graph says all the vertex you traverse at least one and the vertices are happy. And Euler says, whatever come what may, all the edges you have to traverse just once. So till the time you are able to traverse all the edges once, it's a Euler circuit. And till the time you are able to traverse all the vertices at least once, you can skip some edges. That is irrespective. What matters here is that all the vertices has to be covered once. Like you can see, for this I have to traverse these vertices and these edges, they just got skipped, but we don't care because it's in Hamiltonian path, all the vertices got covered. Now, our next important topic is graph coloring. So what is graph coloring? Suppose that GVE is a graph with no multiple edges. A vertex coloring of G is an assignment of colors to the vertices of G such that adjacent vertices have different colors. A graph G is M colorable if there exists a coloring of G which uses M colors. What do you mean by proper coloring? A coloring is proper if any two adjacent vertices U and V have different colors, otherwise it's called an improper coloring.